Welcome to Learner Support Publications. I am Dr. R. Murugan, Associate Professor, Department of Computer Applications, MES College, Marambelli. In this video, we will be discussing Normalization Part 3, Normal Forms 1NF and 2NF. Before discussing normalization, we should be familiar with the process of decomposition of relations. Any database design process involves decomposition. Decomposition refers to the breaking down of one relation into multiple relations. To understand the importance of decomposition, we should first review the idea of redundancy. As we know that redundancy means unwanted and uncontrolled duplication of data. Redundancy not only leads wastage of storage, but also has other side effects such as loss of integrity and data consistency. This redundancy also leads all types of update anomalies such as insert, delete, and modification anomalies. Let us consider a relation examination for storing information regarding students and the marks they obtained in various subjects. Let the relation has the following columns: roll number, student name, subject code, subject name, and marks. We can see some kinds of redundancy in this relation state. Here the student name and the subject name appear many a times. The name of a student repeated for every subject he or she written the examination, and the subject name also repeated for different students written the same subject. This redundancy can be remedied by decomposing the examination relation. The name of the student Christo has been repeated 4 times because he has written examination for 4 different subjects. The name of the student Joel George also repeated 3 times because he has written 3 examination for 3 different subjects. Again, the subject code S101 physics, subject name physics is repeated 2 times because the same subject has been written by 2 different students. So this is called, actually this is redundancy of data. Again, the subject name chemistry also repeated many a times. This redundancy can be remedied by decomposing the examination relation. So we need to reduce this redundancy existing in this table by decomposing the examination relation. We'll see the dependency diagram. So in this dependency diagram, we can identify 3 types of functional dependencies in the relation. Roll number determines the student name, subject code determines the subject name, and the combination of roll number and subject code determines the marks. Or you can say that student name is functionally dependent on roll number and subject name is functionally dependent on subject code, and the marks is functionally dependent on the key attribute. The key attribute is roll number and the subject code. This is a key attribute in this relation. So based on the functional dependencies existing, we can decompose the examination relation into 3 relations. So in this functional dependency, roll number determines student name. Remove student name along with a copy of the determinant, that is the roll number, and store it in a separate relation named student. As you know, determinant is a single attribute or the combination of attribute on the left side of the arrow, the functional dependency. In this functional dependency, subject code determines the subject name. You remove the subject name along with a copy of the determinant, that is a subject code, and store it in a separate table named as subject. And the base table with the remaining attributes formed as another table named exam result. Thus, the base table examination decomposed into 3 relations, namely student table, subject table, and examination result table. And in this decomposed relations, student names appears once and subject names appears once, and these tables are connected with the use of primary and foreign keys. Here the roll number is the primary key, and in subject relation subject code is the primary key. In examination result we have roll number, subject code and marks. And roll number is a foreign key which is used to connect student relation, and subject code is another foreign key which is used to connect to the subject relation. This way we can decompose the base table examination into three different tables. Let us see another concept, lossy decomposition, which means loss of information due to decomposition. Due to bad decomposition, sometimes the joining or rejoining of the decomposed relations may not give back the original tuples of the base relation. Actually, this is undesirable. Let us consider the examination table again. Suppose we have decomposed the examination relation into student relation with the roll number and student name, and subject mark relation with subject code, subject name and marks. We can join two relations into one with the use of common attributes. And in this case, when we join student and subject mark, because these two relations do not have common attribute, when we join these two relations together, we won't get the original tuples of the base relation. Moreover, here the joining process produces spurious tuples, and this is undesirable. The lossless join and dependency preservation property gives the desirable decomposition. Lossless join decomposition means on taking join of the decomposed relations have the same set of tuples as in the original relation, and dependency preservation constraints as per the original relations should not be violated. See, what all the constraints in the base relation we need to preserve after decomposition. So the decomposed relation should give all the constraints which was present in the original base relation. So the decomposition of the examination relation into three relations, student relation, subject relation, exam result relation, is a desirable one. You can join student relation and exam result relation with the use of common attribute, that is a roll number. Again, you can join examination result relation and subject relation with the use of common attribute, that is a subject code. So it is possible to join these relations together and we will get the original, and all the constraints like student number determines the student name and subject code determines the subject name, and a roll number, subject code determines the marks, and all the dependencies are preserved. This is a desirable decomposition because we can join all the three relations with the use of common attributes, and all the functional dependencies present in the original relation are also preserved in the decomposed relation. Normalization is the process of successive reduction of a given set of relations to a better form. Now let us see the term normalization. Normalization is the process of successive reduction of a given set of relations to a better form, and it is a formal technique for analyzing a relation based on its primary key and the functional dependencies between the attributes of that relation. As normalization proceeds, the relations become progressively more restricted, means stronger in format, and also less vulnerable to update anomalies. Again, it is an attempt to eliminate or minimize the problems occurring due to data redundancy over the lifetime of the database. Normalization is the process of making the table free from insert, delete, and modification anomalies and save space by reducing redundancy in data. Now let's see the need for normalization. First, to reduce the redundancy from the table. See, if you reduce the redundancy, then obviously it will compact the data. So obviously the second point is saves spaces. Third point is remove anomalies. So anomalies due to redundancy of data. The fourth point, we can write it as normalization minimizes the null values. And another point, normalization simplifies queries. So if you have the base table with too many attributes, then it will be very difficult to understand or manage the table. But if you can decompose the base table into several tables, then that simplifies the database and can manage very easily. Obviously, it will simplify the queries. It is important for Royal TP type systems. In online transaction processing type systems, the queries like insertion, updation, deletion will be very frequent by the end users, and the relations should be very stronger to manage these types of queries. So the process of normalization is very important for OLTP type systems. The process of normalization can make the structure of the table more easily understandable. Let's see the normal forms. We have first normal form, second normal form, third normal form, Boy Scout normal form, fourth normal form, fifth and higher order normal forms. Each normal form has a specific non-property, and according to that property, we do the process of normalization. Now let us see unnormalized form, a table that contain one or more repeating groups. We'll see how can you create an unnormalized table by transforming the data directly from the information source into table format with columns and rows. That is the table which we are creating directly from the source. Let us consider the property rental details issued by a company named Dream Home Company to one of its customers. The customer John K has taken for rent two different properties on two periods. John K has taken the property PG4 from 1st July 94 to 31st August 96 and the property PG16 from 1st September 96 to 1st September 98. The address of the property, rent, owner number, and owner name of the property also given. Now we'll convert this document into a table form like this. John K has taken two properties for rent. So in the columns, property number, property address, rent start, rent finish, rent, owner number, and owner name, there are two entries. These set of attributes are repeating groups. But the customer number and customer name comes only one in the table. So the property number, property address, rent start, rent finish, rent, owner number, and owner name. These groups of attributes are called repeating groups. This will be repeated for different customers. Now, Dream Home inserted information about another customer, Alain Stewart, in the table, and Alain Stewart has taken three properties for rent. So he has three values in the repeating groups. This table is in an unnormalized form because this has repeating groups of attributes. See, John K has taken two properties for rent on two different periods. So in these repeating groups, he has two rows. There are two values in the repeating groups. And Alain Stewart has taken three different properties for rent. So he has three different values in the repeating groups. Let's see the first normal form. The definition: a table is in the first normal form if it does not contain any repeating columns or repeating groups of columns. Each attribute should contain only atomic values from the respective domain. The table should not contain any composite attributes. So in the given unnormalized table, there are repeating groups. These repeating groups, the property number, property address, rent start, rent finish, rent owner number, and owner name, these columns would repeat for as many properties as the customer has taken for rent. So the customer rental table is not in one enough because it contains a repeating group of columns. So we need to normalize this. Then how to do from UNF to 1NF, that is unnormalized form to 1NF, first normal form. Nominate an attribute or group of attributes to act as the key for the unnormalized table. Identify the repeating groups in the unnormalized table which repeats for the key attributes. We'll see how to transform a table from unnormalized form to first normal form. First, nominate an attribute or group of attributes to act as the key for the unnormalized table. As we know, the key attribute may be a single attribute. Sometimes it may be a combination of more than one attributes. So we need to nominate a single attribute or a group of attribute to act as the key for the unnormalized table. Then we need to identify the repeating groups in the unnormalized table which repeats for the key attributes. Here in this unnormalized table, key attribute is the customer number, and the repeating groups attributes are property number, property address, rent start, rent finish, rent owner number, and owner name. In this unnormalized table, Customer number is the key attribute, and property number, property address, rent start, rent finish, rent, owner number, and owner name are the repeating groups of attributes. There are different methods to transform a table from a UNF to 1NF. We'll see the first method. In the first method, remove the repeating groups by entering appropriate data into the empty columns of the rows containing the repeating data, thereby flattening the table. In the second method, remove the repeating group by placing the repeating data along with a copy of the original key attribute or attributes into a separate table. So this way, this is the repeating group. You can remove the repeating group, place the repeating groups into a separate table along with a copy of the key attribute. Key attribute is the customer number. So remove property number, property address, rent start, rent finish, rent, owner number, owner name. Put it in a separate table along with a copy of the key attribute. So the remaining attributes in the base table are customer number and customer name that you can keep separate. So this is the second method. By using these two methods, you can transform an unnormalized table into first normal form. Now, let's see the second normal form. A relation is in the second normal form if it is in 1NF and non-key attributes are fully functionally dependent on the key attributes. If the key has more than one attributes, then no non-key attributes should be functionally dependent on a part of the key attributes. In second normal form, actually, we need full functional dependency. All the non-key attributes should be fully functionally dependent on the key attributes. Actually, we are checking whether it contains any partial dependency or not. If the table contains any partial dependency, then you can say that it is not in 2NF. And if there is any partial dependency, we need to remove the partial dependency from the table. Now we can consider one of our previous example, examination relation. The table contains a roll number, student name, subject code, subject name, and marks. This table is in 1NF because all the attributes are atomic in nature and there is no repeating group of attributes, but it suffers from redundancy of data. So we need normalization because the student name Christo is repeated many a times, Joel is repeated many times, the subject physics is repeated many times, chemistry is repeated many times. So we can say that there is some form of redundancy in it. So we need to normalize this. Let's see the dependency diagram. In this diagram, the key attribute is the combination of roll number and subject code, and student name, marks, and subject are the non-key attributes. See, clearly we can see the marks. Marks is fully functionally dependent on the key attribute. But the subject name is dependent on roll number only, and subject name is dependent on subject code only. Means student name is partially dependent on the key attribute. There is a partial dependency existing among roll number and student name. And subject name is also dependent only on part of the key attribute, that is a subject code. Again, there is a partial dependency existing. So you can say that the examination table is not in 2NF because it contains partial dependencies. So we need a normalization. 2NF is required. So we need to transform from 1NF to 2NF. Let's see how to transform a table from 1NF to 2NF. Identify the primary key for the 1NF relation. Identify the functional dependencies in the relation. If partial dependencies exists on the primary key, remove them by placing them in a new relation along with a copy of their determinant. So we need to identify the primary key for the first normal form relation, then identify all the dependencies in the relation. If partial dependencies exists on the primary key, remove the partial dependency and placing those attributes having partial dependency into a separate relation along with a copy of the determinant. Here student name has a partial dependency with the key attribute and subject name also has a partial dependency with the key attribute. Clearly we can identify student name is partially dependent on the key attribute. Again, subject name is partially dependent on the key attribute and the marks is fully functionally dependent on the key attribute. So we need to remove student name from this table and put it in a new relation along with a copy of the determinant. And again, you remove the subject name, put it in a new relation along with a copy of the determinant, that is a subject code. And the remaining attributes in the original relation are roll number, subject code, and marks. Okay, now the student relation contains the roll number and student name. Subject relation contains subject code and subject name. An exam result relation contains roll number, subject code, and marks. Now the relation schema are in 2NF. We can check the lossless join and dependency preservation property here. See, we can join these three relations with the use of common attribute. Roll number is common to these two and subject code is common to these two relations. So it is possible to rejoin these relations together, and all the dependencies, student name depended on roll number, subject name depended on subject code, and marks depended on roll number plus subject code. All the constraints are preserved. So this is a desirable decomposition also. Now we'll see one of our previous examples, customer rental relation, and we'll see how to transform that relation from 1NF to 2NF. So that customer renter relation has columns: customer number, property number, customer name, property address, rent start, rent finish, rent, owner number, and owner name. So here to identify the property rented by a particular customer, so the key attribute is the combination of customer number and property number. So then only we can identify from which date to which date a particular property is rented by a particular customer. So the key attribute is a combination of a customer name and property number, which finds the or which determines the rent start and rent finish. But we can identify the customer name has a partial dependency because the customer name is dependent on the customer number, part of the key attribute. So we can say that a partial dependency is existing in this relation. So we can remove the customer name from this table and store it in a separate table along with a copy of the determinant like this. So we can store the customer name into a separate table along with a copy of the determinant. Again, we can see a partial dependency existing. The property address, rent of the property, owner of the property, owner name of the property. These columns are dependent on the property number. That is, there is a partial dependency existing among these columns. So we need to remove the property address, rent, owner number, and owner name from this table and store it in a separate table along with the copy of the determinant, that is the property number. That is, so remove the property address, rent, owner number, owner name, keep it in a separate table, name this table as property owner relation along with the copy of the determinant, that is the property number. We'll see the remaining attributes, rent start, rent finish, and the key attributes, customer number and the property number. And we can store these remaining attributes in a separate relation like this. So renter relation, which contains property number, customer number, property number, rent start, and rent finish. Now these relation schema are in 2NF. Okay, clear. Thank you for watching this video. The next video we'll be discussing normal forms 3NF and BCNF.